Good afternoon. I'm Peter Libin of the University of Brussels, and today I'm going to present my work on Bayesian anytime MTOP exploration. This problem is located in the realm of multi-arm bandits, where we have a set of arms available which we can pull. Each arm is associated with a reward distribution, and when we pull an arm, we receive a reward according to this distribution. Furthermore, we have the mean of this reward distribution for each arm, which we're mostly interested in. And there are different problems that can be modeled in a multi-arm bandit setting. For example, cumulative regret, where we try to pull the arms in such a way that we minimize the regret over time. For example, if you enter a casino, you would like to minimize the money that you lose over time. Or finding the best arm, using through best arm identification, simply finding the arm with the highest mean in a limited number of arm pools or given a fixed confidence. Now, the MTOP anytime exploration problem was introduced by Yun et al. In 2016, and it extends the best arm identification problem into a problem where the objective is to identify the MTOP arms. Also, the objective here is to do anytime recommendation, which means that at any time we should be able to recommend these M best arms. This can be used to model decision problems, also challenging decision problems, where we have a model, an expensive computational model that we can use to test a particular policy, and the different policies can then be modeled as arms. For example, we could use this to maximize the insect distribution for organic farming, and this is an example that we will consider later on in this presentation. Now, the MTOP anytime exploration algorithm that was introduced with this setting is ATL-UCB, and it was introduced in the same paper as the problem came in, and it's a very interesting algorithm, and it remains the state of the art up to date. However, it does not allow to include prior knowledge about the reward distribution, which is unfortunate because this can really lead to an improved learning performance. And to mitigate this, we came up with a solution to try to use Thompson sampling or a Thompson sampling variant to solve the MTOP exploration problem. Now, prior to introducing our new algorithm, we will first introduce Thompson sampling to you. Thompson sampling was presented by Thompson already a long time ago and repopularized by Chappell in 2011, where he showed that it was this very interesting algorithm to use in real-world settings. So we have a prior, so the prior information, the prior knowledge that we put forward about the setting, and we have the history that we observe while we're interacting with the bandit. So we have a set of time steps from 1 to infinity, and we will, at each time step, we will consider the prior conditionalized on the history, which we call the posterior. So we sample from this posterior, which provides us with a sample for each arm. We rank this sample, and we take the top sample and choose the arm that is associated with this sample. This arm we will pull, and we observe a reward, and this reward together with the arm that we pulled, we add to the history that results in a new history. So simply we sample from the posterior, we take the top ranked arm, we pull it, and we add this information that we received to our history. This is Thompson sampling, vanilla Thompson sampling, and it's used to solve the cumulative regret problem. Now, to get some more intuition into vanilla Thompson sampling, let's have a look at this simple example where we have 3 arms and a binomial reward distribution. As you can see here, we have 3 arms, the blue one, the orange one, the green one, and you can see the means of the arms also noted here. So now we will look at the posterior distribution that we have over these arms. In the beginning, we know very little. We only played 5 times, as can be as is shown here. So we only know something about the green one and something about the orange one. The blue one is still completely flat. And we will need to choose an arm to play next. So it can go always. There's a lot of uncertainty with each of these arms. But after 50 trials, our belief over which arm is the best, the most beneficial to pull, starts already to shape. And now we will sample from this distribution and get a sample for each arm and play the arm which corresponds to the sample that was ranked highest. So very often we will play the green one, but also we will explore the orange and the blue one because we're still not entirely certain that these are not the best arm. We continue following this procedure, and the green distribution thins until we have something that will converge towards the delta peak, and we become very certain about the green one being the best arm. Now, boundary focused Thompson sampling is a solution to solve the M-top exploration problem using Thompson sampling. And the first thing that to give you some intuition about this algorithm is that we have now a simple bandit setting. We have 6 arms, and we need to identify the 3 best arms. These are the arms on the right, and we have the arm that we believe to be on the M position and the arm that we believe to be on the M+1 decision. Consider that these are beliefs that we have over the arm. So as we want to identify these arms and be as certain as possible about it, basically we need to focus on the decision boundary that we have here between M+1 and M. This decision boundary is what we should focus on. This is the intuition behind our algorithm. Now, if we just had a look at vanilla Thompson sampling before, we will now add some sprinkles, and this gives us boundary-focused Thompson sampling. A boundary-focused Thompson sampling differs. Rather than always taking the first-ranked arm, we will now choose the arm that is on the M or M+1 position, which is modulated by this Bernoulli experiment. Since it is an anytime algorithm, we will recommend the top arms based on the posterior. So we can recommend at each time. Now, to evaluate the performance of our algorithm, we did some experiments. The first experiment is an experiment that was also in the Jun et al. Paper of 2016, and it considers 1,000 arms. It's quite a challenging bandit environment. And each arm has a Gaussian reward distribution where the variance is fixed. The means of the different arms are increased in a polynomial fashion, and we run our algorithm and ATL-UCB on it to see how our algorithm performs. You can immediately see that ATL-UCB, the green one, curve is much better than the uniform one, what we would expect. And what we are seeing here on the y-axis is the number of arms that are correctly chosen as the top arms, and here is the number of samples that were considered, so from 0 to 14,000. We see that our BFTS performs quite well. After a short burn-in period, BFTS, the red curve, quickly surpasses the ATL-UCB algorithm and outperforms the algorithm quite well. So a next experiment, again, experiment from Jun et al., is the New York cartoon caption experiment, where we want to find the best captions that were entered for a cartoon. This is an example from real data. We have 496 arms, and each arm follows a categorical distribution that was fit using maximum likelihood based on a data set. Again, we have the same evaluation. We have uniform, ATL-UCB outperforms uniform as expected, but also we see that after a burn-in period, here after this period, BFTS outperforms ATL-UCB quite significantly. Now, it's important to say this burn-in period, it might look like this is a problem. It's not such a big deal in our opinion, because in the beginning all algorithms are quite bad, so it's not like that you wouldn't be able to make a well-informed decision at this time with ATL-UCB. The environment is challenging, so you will need some exploration before you can make an informed decision. Now, the third experiment is a new experiment that we introduced, really with the intention to be a very challenging environment. It's what we call the organic bandit. And this bandit maximizes the occurrence of insects to enable organic farming. Because in order to do organic farming, you want, for example, certain bugs to be prevalent in a field, such that they can eat bugs that are eating your crops. Again, we consider 1,000 arms. And from literature, we know that a policy that controls the occurrence of insects follows a Poisson reward distribution. And of course, Poisson reward distribution is quite interesting because it's a quite challenging environment. Challenging because both the mean and the variance are equal. So it's really a very skewed distribution with a very high variance. So it is something that is quite challenging to learn. We increase the means of the different arms in the linear fashion. And now we see that ATL-UCB, the green curve, is not doing much better than uniform. But BFTS strongly outperforms both uniform and ATL-UCB. And shows a very promising learning curve for this problem, which is very interesting because this is because we are able to incorporate the information about the reward distribution that we can learn in such an efficient way. So finally, an overview of the experiments we did. The Gaussian polynomial with fixed variance. We need some burn-in period, but then we also outperform ATL-UCB. The multinomial, again, a burn-in period, and we outperform ATL-UCB. But most spectacularly, we outperform ATL-UCB for the organic bandit, where we have a Poisson reward distribution, which is a particularly challenging distribution to learn in. Then, finally, I want to discuss the theoretical analysis. And while we have a very good performance, an empirical performance, we were not able to prove any bounds on the simple regret. This is of course unfortunate, but it's also not that surprising because many other scientists also run into problems proving this for pure exploration settings with a Thompson sampling variant. So it's something that we also observe in research in literature that this is quite a challenging problem. But we were able to provide some guarantees, and this is not in the paper, but I really want to communicate this here now, that if we consider a relaxed version of the BFTS algorithm, which we dub delta BFTS, where we add an amount of random exploration, this can be very, very little. For example, delta spread over all the arms can be as small as 0.05. So just a very small amount of random exploration, we can provide some guarantees. Changing the algorithm to incorporate this is simply changing this rule. Rather than always taking the m or the m plus 1 arm, we add some random exploration here. So it's a very trivial extension of the algorithm, but it allows us to provide some guarantees. Not a tight bound yet, so it would be very interesting for future work to see that we can prove a tight bound for this problem. So to conclude, we developed the BFTS MTOP recommendation algorithm. It's a new algorithm and it outperforms ATL UCB. We were not able to provide any guarantees, any tight bounds yet, but we were able to provide an algorithm, a relaxed version of the algorithm called Delta BFTS, for which we were able to provide some guarantees. And finally, I want to acknowledge the people that I collaborated with on this project, both from the University of Brussels and the University of Leuven.